Hey everyone, ready to dive into something pretty cool. We're tackling physically based shading today. The stuff that makes CGI in movies and games look crazy real.
Yeah, and we took our hands on some really juicy info from the pros themselves, ILM and Triace, plus a stack of course notes that break it all down. Should be fun.
Awesome. So we're talking light, right? But not just like light bulbs. We're going way deeper to like the actual physics of light as a wave. I'll be honest, my physics is a little rusty.
Wow, what does that even mean for computer graphics?
Okay, so imagine like ripples on a pond, right? Yeah. Light's kind of like that. Those ripples have a distance between them as a wavelength, just like different colors in a rainbow. Light has different wavelengths. And here's the kicker. Our eyes only see a tiny bit of all those wavelengths, this range we call visible light. So it's like our eyes are tuned to one radio station, but for light. And computer graphics has to play that specific station to trick our eyes.
Exactly. It's all about recreating how light from that visible spectrum bounces around, hits stuff. That's the key to making computer images look believable, not fake.
Okay, that clicks. Now, these notes mention homogeneous and heterogeneous media.
Uh,
Help a guy out. What's the difference and why is it important for light?
Good one. Picture this. You're shining a flashlight through a glass of water. That beam goes straight. Yeah.
Huh?
Water's homogeneous. It's the same throughout. Now shine that flashlight through a cloud. Totally different, right? The light goes everywhere. That's heterogeneous. It's made of tons of tiny things, like those water droplets in a cloud that bounce the light around.
So homogeneous is like driving on an empty highway, and heterogeneous is like, I don't know, navigating Times Square at rush hour with light bouncing off all the billboards.
Perfect analogy. And just like in Times Square, that light bouncing around in those different directions is called scattering. Super important for realistic clouds, smoke, even skin, all that good stuff.
Wow, never thought about it like that. So you've got how light travels through stuff, but then there's how it hits surfaces, right?
Yeah.
Those surfaces aren't always smooth, are they?
You got it. Even things that look smooth to us, like this table, actually have microscopic bumps and grooves.
So what happens to light when it hits all those tiny imperfections?
Okay, imagine the difference between a mirror and, say, a wooden table. With a mirror, you get that perfect reflection, super clear because it's smooth, but the table, all those tiny bumps on the surface make the light bounce off in different directions so the reflection is softer, more diffuse. That's surface roughness, key for realistic CG.
Mind blown. Okay, so to recap, we've got the wave nature of light, how it goes through different stuff, and then the roughness of surfaces, all impacting how we see things. That's a lot to simulate for CGI. That's got to involve some heavy math, right? Is that where BRDF comes in?
Bingo. BRDF stands for Bidirectional Reflectance Distribution Function. Sounds crazy, but think of it like a set of rules that tell the computer how a surface reacts to light from all angles.
So it's like the instructions for how a material reflects light with all these different ingredients for color, roughness, and all those unique light-bouncing properties.
You're getting it. And a big ingredient in that recipe is Fresnel reflectance.
Wait, isn't that the thing where, like, if you look straight at a window, it's see-through, but from an angle, it's a mirror?
Exactly. Fresnel reflectance is how much light a surface reflects depending on the angle you're looking at it from.
That's wild. So that's got to be in the BRDF to make stuff like glass or water look real.
We're 100%. Without Fresnel, CG glass would be a dead giveaway. No reflections, no realism.
Right, it just look off.
Yeah.
So you've got the BRDF telling the surface what to do with the light, Fresnel handling the angle.
Yeah.
Anything else in this equation that makes things look extra real?
Oh yeah, one more biggie. Shadowing and masking. Basically how the BRDF handles stuff blocking light. Without it, you'd have objects looking weirdly lit, even in shadow.
Yeah, things would look super cartoony.
For sure. Shadowing and masking make sure the light behaves realistically. Nice, accurate shadows and no weird glowing where there shouldn't be.
Okay, starting to wrap my head around this, all these little details adding up. It's a lot.
Yeah.
But how do we go from equations and concepts to like actually using this stuff in games and movies? So we've got the science of light down, but how do game devs and filmmakers actually use this stuff? Like simulate every photon bouncing around seems kind of impossible.
Yeah, you're right. It's a huge challenge, especially for games that need to render everything in real time. That's where compromises and clever tricks come in.
And one of those tricks is this Blinn-Phong shading model. I feel like I've heard of that, but it also sounds kind of old school.
It's a classic for sure, goes way back to the 70s, but don't let that fool you. Blinn-Fong's gotten a serious upgrade over the years.
So it's like taking a classic car, keeping the cool look, but giving it a modern engine.
Exactly. It's still based on the same fundamental ideas, but with a bunch of tweaks to make it more physically accurate.
Makes sense. Like, why reinvent the wheel when you can just, you know, Give it some fancy new tires.
Right. And this Tri-Ace document, they talk about how they've customized their Blindfang model even further. Like they made specialized versions for different materials.
Now we're talking. They mentioned something about anisotropic shading. What is that exactly?
Okay, imagine looking at a piece of brushed metal. See how the highlights kind of run in one direction following the brushstrokes?
Yeah, yeah.
That's anisotropy. It means the material's properties, like how it reflects light, change depending on which way you look at it.
So it's like giving those virtual materials a sense of direction, like the grain in wood or the weave of a fabric.
Spot on. Those little details make a huge difference. And Trias took it even further. They even implemented spectral and metal variations of their Blindfang shader.
Hold on, spectral shaders. Now that sounds seriously complex. What's the deal with those?
Remember how we talked about light having different wavelengths? Like the colors in a rainbow? Well, spectral shaders actually take those individual wavelengths into account when calculating how light interacts with a material.
Whoa, so it's not just treating light as one thing, it's breaking it down into all its little color components.
Precisely, and that's super important for getting those really accurate, nuanced colors, especially with materials that interact with light in weird ways. Like think about iridescent surfaces, those shimmery, color-shifting effects.
Oh, right, like a soap bubble or some gemstones?
Exactly.
Yeah.
That's all about how those materials reflect and transmit different wavelengths of light.
That's incredible. So spectral shaders are all about capturing that super detailed color shifting action. What about the metal shaders? We touched on metal earlier. What makes it so hard to render realistically?
Metals are tricky, man. They reflect light differently than other materials, plus they absorb most of it, which gives them that shine. Even a tiny mistake in the shader and it just looks fake.
So it's not enough to just make it shiny. It has to be that specific kind of metallic shine.
Right. And it gets even more complicated when you start thinking about all the different types of metals, each with its own way of reflecting light. Tri-Ace's metal shader was all about simulating those complex interactions accurately so they could create a wider range of convincing metals.
So we've covered how to shade individual materials, but what about lighting the whole scene? Like where do environment maps and ambient lighting fit into this physically based world?
Ah, great question. Imagine you're standing in a room, you've got the light bulb, sure, but the light bouncing off the walls and furniture also affects how you see everything, right? Environment maps do that for CGI.
So instead of just one light source, you're simulating how light would naturally fill up the whole environment.
That's the idea. And environment maps are key to making that happen. They're like panoramic snapshots of the surroundings, capturing the light coming from everywhere.
Cool. Speaking of cool, the ILM document, they used to use these chrome balls to create environment maps, like an actual ball. Tell me more. That's fascinating.
It does sound kind of wild, right? But it's actually pretty ingenious. They'd put this chrome ball on set and photograph it from all angles. Because it was so reflective, those photos captured a distorted view of the entire environment.
That's so smart. Like a low-tech way to get a 360 view before 360 cameras existed.
But the document also mentions HDRI. Is that how environment mapping is done now?
You got it. HDRI, or high dynamic range imaging, is all about capturing the full range of light intensities you see in the real world. You ever notice how a normal photo loses detail in the really bright or dark areas? HDRI fixes that. So it's like having a super-powered camera that can see all the detail, even in those blown-out highlights and crushed shadows.
Nailed it. And that's crucial for realistic lighting because real life has this huge range of light and dark. ILM started using HDRI a lot in movies like Iron Man and Terminator Salvation to create those epic outdoor scenes.
Okay, so you've got these awesome HDRI environments, but how do you actually use them when you're rendering?
That's where pre-filtering comes in. Sounds weird, but you actually blur those HDRI maps in a specific way.
Blur them. Why mess with something that's supposed to be super detailed?
Think about it. A rough surface scatters light more, makes the reflection softer. By pre-blurring the environment map to different degrees, you can simulate how surfaces with different roughnesses would reflect that light.
Ah, I see. So you're basically doing the math beforehand for how those HDRI environments would look when reflected off different materials.
Exactly. Saves a ton of processing power later on. Pretty neat, huh?
Crazy clever. We've gone from light and materials to equations, and now to actually putting those equations to work with stuff like Blindfang, environment maps, HDRI. It's amazing how it all connects. But I'm ready to see this stuff in action. Can we dive into some examples of how these techniques have changed the way films and games look? Right, you've sold me on the theory, but I'm ready for the good stuff. Hit me with those case studies. Show me how physically based shading changed the game, like literally.
Okay, so ILM's journey to realism is a great place to start. They've been pushing the boundaries of VFX forever, so seeing how they adopted these techniques is fascinating.
Yeah, the ILM document mentions Pearl Harbor, which had some amazing water, right?
Yeah.
But that was before they went all in on physically based shading, wasn't it?
Right. Pearl Harbor was big because they introduced ambient occlusion, which made those scenes look way more three-dimensional, by simulating those subtle shadows where surfaces meet. But their shading model was still pretty traditional back then.
So they were dipping their toes in the water, literally, before diving headfirst into physically based shading with Iron Man.
Exactly. Iron Man was a turning point. They had to create this super realistic metal suit, and it had to look believable in any lighting. That's what really pushed them to go all in on physically based shading and image-based lighting.
Yeah, and the document goes deep on that, their quest for better metal. Apparently, it's way harder than it sounds to make CG metal look right.
Oh, it's notoriously tricky. Metal has this whole dance of reflections and absorption that's tough to capture. ILM had to develop all these new techniques and shaders to get it right.
They even made a special anisotropic specular function just for the brushed metal on Iron Man's suit. That's dedication. It's no wonder those visuals still hold up so well.
For sure. And they didn't stop there. On Terminator Salvation, they took things even further, developed a whole new energy-conserving shading system within RenderMan, their main rendering software.
Okay, gotta ask, what does an energy-conserving shading system even mean?
So basically, it means their shaders got a whole lot more realistic, especially when it came to how much light a surface could reflect. Before, some shaders might have reflected more light than they received, which, isn't physically possible, makes things look kind of off.
So it's like making sure your virtual lights are all energy efficient. No more cheating the laws of physics.
Pretty much. That focus on energy conservation, plus a technique called importance sampling, which made their ray tracing way more efficient, led to a huge jump in realism.
Important sampling.
Right.
That rings a bell. It's about speeding up those crazy complex calculations.
Yeah, I got it. Working smarter, not harder. Even with all those insane CGI details, it makes you realize how much artistry goes into this stuff. It's not just technical, it's about understanding the science and using it creatively.
Totally. And speaking of creativity, the ILM document emphasizes how important it is to work closely with the filmmakers, especially the gaffer, the lighting guru on set.
Oh yeah, collaboration is key.
They even have a whole section on set etiquette, which I got a kick out of. But it makes sense. You don't want to be the VFX person holding up the shoot just to get one perfect reference photo.
Right. Be efficient, respectful of everyone's time, and work together. They had this great line, when in doubt, shoot refs.
Love it. You never know what detail might come in handy later when you're building that scene in the computer. Capture everything. Speaking of capturing information, what about Tri-Ace? What do they teach us about physically based shading in games?
Oh man, Triace is doing some seriously impressive stuff, especially considering the limitations of real-time rendering. They don't have the luxury of those massive render farms that ILM uses.
So how do they make it work in a real-time environment like a video game?
Well, remember those customized Blinfong shaders we talked about? The ones specifically for different materials?
Yeah, the anisotropic, spectral, and metal shaders, right?
Exactly. That was huge for them. By tailoring their shaders, they were able to get better results with less processing power.
So it's about working smarter, not harder, again.
100%. Plus, they use pre-computed lighting data whenever possible. In games, you can't spend hours rendering a single frame like you can with film.
Right. Got to keep things moving for the player.
Exactly. So they pre-calculated as much of the lighting information as possible beforehand. That let them achieve a surprising amount of realism without sacrificing performance.
It's amazing how these techniques are used differently depending on what you're making. But it shows that realism in computer graphics is always evolving. What works today might be obsolete tomorrow.
Oh, absolutely. And as technology gets better, who knows what we'll be able to create? The line between real and virtual is getting blurrier every day. That's what makes this whole field so exciting.
It really is. It's this constant drive to innovate, to find creative solutions to complex problems. We've covered a ton of ground today, but it's just the tip of the iceberg. But now when you see those amazing effects in games and movies, you'll have a better understanding of what goes into them.
Exactly. Those stunning visuals, they're not magic. They're the result of talented people combining science and artistry in really cool ways.
Well said.
And on that note, we've reached the end of our deep dive, but this is just the beginning of your journey, right? You're armed with all this knowledge now. So next time you're blown away by some incredible CGI, take a moment to appreciate the science, the artistry, the sheer problem solving that went into making it happen. Until next time.